Geometry, Lesson 9.4. We're moving on from pyramids and cones to prisms and cylinders. Here's a slide with many of the formulas for this lesson. These are your specialized formulas, so be sure to use those whenever possible. Have them in your notes next to you. So a little bit of background. The area of a two-dimensional region is the number of units needed to cover the region completely. So this is the definition of area. For a three-dimensional solid, its area consists of both a surface and its interior. In the last two sections, we've been using formulas for the number of square units needed to cover the surface of a three-dimensional object. Now we will move on to learn how to calculate the volume of the interior of a three-dimensional object. So, by definition, a cubic unit is a cube whose edges measure 1 unit, which could be a cubic centimeter, cubic foot, cubic yard, cubic meter, or any other cubic unit. So we've looked at diagrams like this before. You can see on the base it's 1 by 1, the height is 1, but what we haven't done is talked about the inside of this cube. The inside of the cube is what we call the volume. The volume of a solid is the number of cubic units needed to fill its interior completely. So if I were to pour sand inside of this cube, that's what we are now going to be estimating. We have some postulates. Postulate 9.4.1, the volume postulate. Every solid has a volume given by a unique positive real number. That means if you're working on a problem and you get a negative number for the answer, something is off. So, just like we have with measurement, we'll have positive real numbers for answers. Postulate 9.4.2, the volume of a cube postulate. The volume of a cube is the length of one edge cubed. So, volume equals the length of the edge to the third power. Remember, this is cubes, so we have the base, the height, and the inside that we're discovering. For area, we just had the base and the height, so area would have been squared. All of our volume postulates and theorems, formulas that we'll use, deal with cubed. Postulate 9.4.3, the volume addition postulate. If the interiors of two solids do not intersect, then the volume of their union is the sum of their volumes. This is very similar to our angle addition postulate, to circle addition postulates, all of the postulates we've done before. This postulate is giving you the background to allow them to be added together. Postulate 9.4.4, congruent solids postulate. Congruent solids have the same volume. So if you have two solids that are congruent, they're going to have the same volume. This just makes sense. However, we'll have a little tweak on that in a moment, and that's why we have a postulate for this. So when we're calculating volume, we'll calculate by measuring the base times the height, and we'll actually have a formula which is length times width times height. So sometimes you'll see this formula as small b, small h, big H. So you'll have to get used to that. Be sure you're following whether to do small letters or large letters with your formulas. How many cubic units are required to build the right rectangular prism? Each layer contains 4 times 3, or 12 cubic units, and there are 6 layers. So each one of these layers, here's layer 1, has 12 cubic units. Layer 2 has another 12. Layer 3 has another 12, and so forth. And there are 1, 2, 3, 4, 5, 6 levels. So each one of these is a cubic unit as far as measurement also. So we have a height of 6 here. We have a base of 4 times 3. So 4 times 3 is 12. We'll have a total of 6 times 12, which is 72 cubic units. So there are 72 blocks in this figure. Theorem 9.4.1. A cross-section of a prism that is parallel to the bases of the prism is congruent to the bases. If you have a prism and you cut it with a plane perpendicular to its base, that plane within this prism will be congruent to the base and to the top. We did this in our last chapter where we talked about cutting the figures with planes either perpendicular or vertical and so forth. So this cross section, no matter where you cut it here inside of this prism, will be the same area as the area of the base or the area of the top base. Now what happens when we tilt one of these figures? For any two solids with the same height, if all planes parallel to a fixed plane form sections having equal areas, then the solids have the same volume. So when we have an oblique figure, we can no longer drop an altitude inside that will work or use the side length that will work. We have to drop the altitude outside. This height on this figure is the same length as this height on the right figure. The width is the same and the length is the same. If this is true, then the volume will be the same on both of these figures, even if this one is tilted or oblique. And its cross-section will also be equal in area to its bases. This is called Cavallari's principle, and it can be used for other figures also. Theorem 9.4.2. The volume of a rectangular prism is the product of its length, width, and height. So here's the formula, and we already expressed it as a postulate. Now you have the theorem for it. This is the formula, the basic formula that we'll be using. Theorem 9.4.3. The volume of a prism is the product of its height and the area of its base. So this is actually the same formula. So for most of our problems, we'll find out what type of base we have, like we have been doing, and then we'll multiply that base total by the height, and that'll give us our volume. So here's our first example. Find the volume of a regular prism. Let's first take a look at our figure. Our figure has a hexagonal base. So that means to solve for the base, what we do with a hexagon is we split it into 6 equilateral triangles. We solve the area of one of the triangles and multiply it by 6. So the area of that triangle that we split this base into is square root of 3 over 4 sides squared. That is the area of an equilateral triangle, and there will be 6 triangles in that hexagonal base. It is only with this hexagonal base that we do this. 6 and 4 can both be reduced by 2, so doing so we end up with 3 square root of 3 over 2, and the sides are 8 centimeters, so it's times 8 squared. That's 3 square root of 3 over 2 times 64. 3 times 64 is 192. 192 divided by 2 square root of 3 is 96 square root of 3 centimeters cubed. And sorry about that, that's really centimeters squared. This is the area of a base. So, we now have the area of our hexagonal base, and we can go forward with our volume formula. So volume equals base times the height. So we substitute our value for the base, which was 96 square root of 3, and the height is 14 square root of 3. So we multiply them together, and most of you don't do this step anymore, but so you can visually see it, 96 times 14 is 1344. Square root of 3 times square root of 3 is 3. These two numbers multiply together to be 4,032 centimeters cubed. So volume is cubed, area is squared. Theorem 9.4.4. We had a picture before that was prisms. Now we have cylinders. And Cavalieri's principle applies here also. So the volume of a cylinder is the product of its height and the area of its base. So we have the same formula, but because this is a circular cylinder, we can now make it more specific. So the base is area of a circle, which is pi r squared. So instead of volume equals base times height, it's now volume equals pi r squared times height. Example 2. We have a circular cylinder, has a radius of 5 inches and a height of 12 inches. So let's use our formula. Volume equals pi r squared height, that's pi 5 squared times 12. 25 times 12 pi, 25 times 12 is 300, 300 pi inches cubed, it's approximately 942.5 inches cubed. Example 3, this is one of those problems where they ask you to back solve. So, to what height would 22,000 feet cubed of corn fill a silo? For those of you who don't know what a silo is, it looks like a tall cylinder that would be on a farm full of corn with a diameter of 20 feet. So if it has a diameter of 20 feet, we need a radius. 20 divided by 2 will be our radius of 10. So we substitute, when we're back solving, all our known values into our formulas. Be sure to write the formula down. So the volume was 22,000. It's pi radius, which is 10 squared, times the height. Remember, we're solving height. If we expand, we have 22,000 equals 100 pi height. 22,000 divided by 100 will be 220 pi height. And to solve for h, we'll divide by pi on both sides. And 220 divided by pi is approximately 70 feet. Now this won't be cubed or squared because it's one of the pieces of the formula. So your homework will be on pages 417 through 421, numbers 1 through 8, 12 through 13, 15, 17 through 21, 23, 44 through 48, which are review. I'm going to help you with some notes. The homework is difficult in this lesson. Please contact me if you're having any troubles. What I can do if you contact me is I'll give you the answers to the even problems. And if you don't get that answer, try to solve again. And if you still don't get that answer, contact me and I'll walk you through it. So homework examples number 1 through 8, be sure to use the most specific formula. So have your formula sheet next to you. Use the specific formula for your situation. In number 4, just so you're aware. The problem actually gives you the whole base figure. You don't have to solve for the base. Number 17 is actually asking how many boxes. Each box is 1 cubic foot, so whatever number your answer is will be how many boxes. Number 19. This is a little difficult visually, so I'm going to help you solve. We're going to use the P theorem to solve for the slant height and the height. Looking at this figure, you can see that they have two dotted lines. One is a diagonal of the base, and another one is a diagonal inside of this prism. So we're going to solve first for this base because we need the pieces to be able to solve for the slant height and the height. So we'll begin by making a triangle, and this triangle will be a 90-degree triangle, so we can use the P theorem. And this looks like a 1 squared. It's not 1, it's slant height squared. So I'm looking at this bottom triangle, and we're actually working on the base. So it's this side, the short side here, 1 squared plus 3 squared equals 5 squared. I'm sorry, and I said 1 squared, didn't I? This is L squared, the slant height. So L squared equals, and I'm just reversing my equation to solve for L. L squared equals 5 squared minus 3 squared, which is 25 minus 9. So L squared equals square root of 16. So the slant height L will equal 4. Now to solve for H, which we need for our formula, we now have L, which is slant height, is 4. Now we're going to solve for H. It's H squared plus 5 squared equals 8 squared. So it's height squared. It'll be height this piece. Let me write that in there for you. Here's the height, and we're looking at this triangle. There's the height. There's the bottom of the triangle. There's the hypotenuse of the triangle. So we have height squared plus 5 squared equals 8 squared. I'm going to switch this around, so it's height squared equals 8 squared minus 5 squared, which is 64 minus 25, and H squared, or H equals square root of 39. So we can now plug these numbers into our formula. 4 and the 3 is this piece right here. So 4 times 3, length times width times the height, square root of 39. The volume would be 12 square root of 39 feet cubed, but what we were actually solving for was our slant height and our height. And there's the answers for that. So that's a little difficult just because we haven't done these visually before. What I usually try to do is redraw the triangles. Let's look at number 21, a similar situation. We need to use the 45, 45, 90 triangle ratios to solve the length of an edge. So, and it's amazing to me how these things slide over on my slides. Sorry. All right, so we have a cube. They tell you it's a cube, and it has a diagonal on the base. So that is 10 yards. So that's your hypotenuse. So I've redrawn the triangle. There's the hypotenuse there. And what we have to do is solve for the side lengths so we can use our formula for a cube. So here's the ratio, x, x, and x square root of 2. Now 10 would be the x square root of 2. So then x would be 10 divided by square root of 2. And if you remember, we always normalize the problem when there is a ratio dividing on the bottom. So we multiply by 1. And we have 10 square root of 2 over 2. 10 can be divided by 2. So x equals 5 square root of 2. We now have the side length. It'll be the same side length on the other side of the triangle because this is a 45, 45, 90. So now we can put our answer into our volume formula, and 5 square root of 2 times 5 square root of 2 would be 25 times 2, which is 50, and that 50 times 5 would be 250, and we'd have another square root of 2 left over. So it's 250 square root of 2 yards to the third power, or cubed. So once again, contact me if you need any help with this unit, and I'll send you the answers if need be for your even problems.